Okay. All right, so let's begin where we left off last time. We were talking about period. So remember, we say capital T is what we call it for the period. That's the time for one cycle, one oscillation, one full oscillation. Now, we also talked about frequency. Frequency small f, that's going to be 1 over the period. Okay. So remember, frequency is the number of cycles per unit time, or per second. So that's why doing 1 over tau, or 1 over capital T is going to give you the frequency. So the units for period is obviously seconds, but the units for frequency is inverse seconds, 1 over time, or we also call this hertz, which is number of cycles per second. Okay. Cycle is not really a unit of anything, just saying it's clarifying that it's one time that goes through an oscillation. Okay, any questions about this? All right, so now we did a little demo showing you that we can think of oscillations as a little particle going around a circle. You know, it starts here, it goes around, right? And then we said we can write down the x-coordinate. So I didn't really draw this out in my. So let's say moves to here, from here to there, and that's theta. So then the x-coordinate would be the radius times cosine of theta. And now I can think of this theta as just increasing with time as it goes around like this. Now, because I can think of this as an angle to describe the oscillation, we're also going to define what's called an angular frequency. Angular frequency. So in other words, as I go through one cycle, the angle will go through 2 pi radians. Everybody good on that? Okay. So the angular frequency, omega, is the number of radians per unit time, or per unit second. Number of radians per unit time, or per second. Okay, so if I want to switch from frequency, which is the number of cycles per second, and I want to get angular frequency. So I want something that converts from angular frequency, this is radians per, let's say, second, just make it concrete. But then this frequency, f, is the number of cycles per second. I need to multiply by 2 pi, okay, because I'm going to do 2 pi radians every time it does a cycle. Everybody's okay with that? Does that make sense? All right. Okay, so that's the connection between the small omega, the angular frequency here, and the regular frequency f. So because f is equal to 1 over the period, that means omega, the angular frequency, is equal to 2 pi divided by capital T. Okay. Now, yeah, this is exactly the sentence I was about to say. Okay. So I've switched the words on you, but you've seen the symbol before. We've called this angular speed. And you can see the connection here if I think of the oscillation as the particle going around the circle, right, and then this x-coordinate will be how it's oscillating, just like the little demo, okay? If I think of it this way, then the omega is really the angular speed, how quickly theta is changing in time, okay? So in other words, if I go back here, something like r cosine omega times t, this is exactly the correspondence. This is what would happen, that the theta is just increasing linearly with time, and the rate is the speed, the angular speed is omega. Okay. Now, we try not to use the word speed because in the case of the mass on a spring, there really is no circle. It's just going up and down. And so if you talk about angular speed, that might be somewhat confusing because people will be looking for angular, things moving in circles. So we use the term angular frequency, but it's actually the same thing as angular speed, which is k. Any questions? So the same thing. So omega is, so let me just write it out clearly, is angular frequency, which is the same as angular, you can say angular velocity or angular speed. We're only going to be talking about positive values. Okay, any questions? All right. Now let's go back to analyzing what's going on mass on a spring. And we're going to get into the details of what the solution or the behavior is going to be. So just out of curiosity, how many of you have seen a differential equation before? Some of you have. Okay. All right. I was debating whether or not to talk about that. I'll mention it, but I won't make it the focus of the lecture. Mass and spring. Okay, so we have, I'm going to draw it horizontally because horizontally with the frictionless table is a little bit easier to understand. So we have our spring with some relaxed length. So this will be the equilibrium position. So there's some mass m. This direction here is the positive x-axis, and this is the equilibrium point. All right, now remember with a spring, you can stretch it or you can compress it. Either way, it tries to bring the mass back to its equilibrium point. So let's say we stretch it. In this case, x is positive. And then there's going to be a force that goes like this. That would be the force F. Sorry, I ran out of space a little bit here. And the x component of this force will have a minus kx, where this k is the spring constant. Questions about this? All right. So there's going to be then some acceleration due to the force of the spring. It's always going to try to bring it back to its equilibrium point. And at this point, if we were more, if this class had a little bit more calculus involved, we were doing differential equations, what I would do is I'd write down what is the acceleration on the mass. Okay. You say F net is equal to ma, right? I know the force net will be equal to the mass times the acceleration. And then I would say, okay, then the acceleration is the time derivative of the velocity. Okay. But then the velocity is the time derivative of the position. And so in the end, I would get acceleration. The whole thing is about acceleration. The acceleration would be the double derivative of the position. Okay. But then the acceleration is also going to be the force divided by the mass. Okay. And so here's the force divided by the mass. I would end up with an equation that would link this thing divided by the mass and the double derivative of the velocity. I'm not writing it down because I don't want people to think that that's where you're going to test you on in the quiz. That's a little, maybe probably, if you're taking calculus 1 right now, this is a little too far ahead in calculus. Okay. So you would end up with the double derivative of x is equal to minus k over m times x. Okay. So if you know what this means, all this stuff is doing. Okay. The double derivative of x, that will be the acceleration, is equal to the acceleration. I said I was going to write it down, now I'm writing it down. I'm sorry. Okay. It's going to be the force x, okay, divided by m. And I plug it in here, I get minus k over mx. And so now you need to try to solve an equation that the double derivative of x with respect to time is equal to something minus k over m times x. Okay, the answer to that, what's called a differential equation, is cosines and sines. That's all it is. And so that's why we just start with cosines and sines, okay? So don't worry about this. That's not necessary. Okay, so this is the basis of simple harmonic motion. And the solution, one particular solution, is exactly what we discussed last time. It's some amplitude A times the cosine of omega tau. I keep saying tau. There's no tau in this whole lecture, and I don't know why I keep saying tau. T. Okay. All right. By the way, even if you don't know differential equations, one thing maybe you should know, right? Oh, right. Those of you doing calculus 1, you know how to take derivatives of cosines, right? You've done that, right? Everybody knows that. So what's the derivative? If I do the derivative of cosine of t, by the way, what do I get if I take one derivative of cosine of t? Yeah, negative sine. Okay. Now, let's just do some refresher calculus so that you can see. I'm going to write down some equations. I'm going to give you the answers of things. If you remember this, it will kind of make a little bit more sense that I'm not pulling things out of the hat. So let me just refresh your memory. Okay, if I take the derivative of cosine of omega t, you know what that would give me? Then, right?
Negative omega.
Yeah. So exactly. So you would have to. There's going to be, because instead of, it's not just a function of t, it's a function now of omega times t. Yeah. You have to change. You have to do this chain rule and multiply by the derivative of the variable, which is omega t. Everybody's remembering that, right? So there's going to be an extra omega, and then so I have sine of omega t. All right, we're going to be doing things like that. Now, while we're along doing this, if I have the sine of omega t, then this is the derivative of sine is obviously then cosine, but then this omega is sitting out there, so it has to come out in front. So it's omega cosine of omega t. Okay, thank you. Okay. All right. Good. Any questions? All right. So these will come up in just a moment. So we said that A is the amplitude. All right. It's the maximum value that this can take, and negative A is the minimum or the lowest value. And now, let me tell you that the angular frequency, and I'm just going to give you this answer, omega is given by, for the case of the mass on a spring, there's a formula. omega is equal to k square root of k over m, where this is the spring constant. And m is the mass. Okay. I just pulled that out of the hat. Now I'm going to, for those of you who can follow these steps, I can show you where this comes from. Okay. So I took one derivative of cosine omega t, and I get minus omega sine omega t, right? Suppose I take two derivatives of cosine omega t, then I would have to take a derivative of this guy, right? Does that make sense? Because this is one derivative, I need to take two derivatives. And then I know the derivative of sine omega t, it's omega cosine omega t. But then there's this extra minus omega that sticks out here. So if I take two derivatives of cosine omega t, I end up with, let me just tack that on here. If I take two derivatives, double derivative of cosine omega t, I end up with minus omega squared cosine omega t. All right? So if I take two derivatives of the cosine function of cosine omega t, I get minus omega squared cosine omega t. So the function comes back again. That is actually exactly what we want here. We have this, what's called a differential equation, that the double derivative with respect to time of x is equal to some negative constant times x, and that's exactly what cosine does for us. So that's actually how you can guess the solution to this differential equation. So if you've never seen a differential equation, this is your first differential equation. I'm showing it to you. You're not going to be tested on it, but it's sort of a big deal. It's coming up in your future. So I'm trying to give you some foresight into that. Okay. Now, if you now make further the connection that this constant out in front was minus k over m, and then if I take two derivatives of this cosine omega t, I get minus omega squared. And you say, k over m with a minus sign, omega squared with a minus sign. I can solve that. Omega is equal to the square root of k over m. You see that? Okay. So that's where this comes from. Okay. So you don't need to remember all these steps, but I'm trying to show you that I didn't make all this stuff up. Okay. So the angular frequency is the square root of k over m. Any questions of this, about this? Pretty good? Okay. So does anybody remember what the units for omega would be? 1/2 second. Yes, 1/2 second. Or radians per second. Now, radians is kind of not one of these units that can sort of go away because it doesn't really mean anything. The only reason we write radians is because we have another unit called degrees, and you need to know which one you're using. So that's why we write radians, right? So if we only use radians all the time, then we'd forget about writing the word radians. Okay, then you can check that the units come out right. And it's maybe not so trivial. So the spring constant is, okay, so the spring constant, where does that come from? It's the formula we have here. This is in newtons, this x is in meters, and so the spring constant will be newtons divided by meters, okay? So newtons divided, what I want to do is I want to show you that the units actually work here. Okay, so K, the units will be newtons divided by meters, but a newton is kilogram meters per second squared divided by meters, and so it's kilograms per second squared. Okay. So now if I divide by m, which has units of mass, then K over m, the units of K over m would then be this km, this kilograms goes away, 1/2 seconds squared. Everybody's good on that? And now if I take the square root of that, it will give me 1/2 seconds, which is the units for omega. The only reason I tell you this is because if you want to know how I remember this formula, I have trouble remembering whether it's k over m or m over k, because we do one or the other. And if you want to do what I do, I always check the units where the seconds are. and I look at the spring constant, and I notice that the seconds are in the denominator, and so it's not square root of m over k. Okay, I'm just giving you this hint because this is actually really what I do to try to remember this formula and not screw it up. And the reason why sometimes I forget this formula is because sometimes we do the following. Okay, so for example, let's calculate what would the frequency, the regular frequency would be from this formula. The regular frequency is going to be the angular frequency, and you going from radians to cycles, so you're going to have to divide by 2 pi radians. Right? Everybody's with me going one way or the other? This is cycles per second, this is radians per second. This guy has the extra factor of 2 pi because it's counting radians. Okay? Am I making sense? Is this? Okay. So it's divided by 2 pi. So then the formula for the frequency, so this is the regular, this is the plane frequency, while omega is the angular frequency. Then the formula will be square root of k over m. Okay, and then there's a 1 over 2 pi. I don't know where to put it. Let's put it right in front. 1 over 2 pi. Now, if I wanted to write a formula for the period, then I would flip everything over. So then I would have 2 pi. And then this would be flipped over. I would have the square root of m over k. And so in this case, you need something with units of seconds. And that's how I keep track of which way it goes, by just looking at units. If you have your equation sheet, that'll be there as well, the equation, the quiz 6 equation sheet. All right, any questions? Okay, so now let's suppose we have the mass on the spring, and okay, let's say this is equilibrium. We stretch it an extra distance, x0, let's call it x0 for the initial, and then we let it go. Then it would do this oscillation back and forth. Okay. So that would be the initial position starting from this. So let's just say that. So let's say if the mass is pulled to a displacement of x0 from equilibrium and released from rest, meaning you don't give it a kick, okay? You just let it go, release it from rest. Then what you'll find is that the amplitude A is just equal to x0. Right? What I'm saying is, very simply, let's do it this way. Here's equilibrium. Right. And let's say I bring it up here, so x1 will be, maybe call it y instead of x. x0 or y0. Then when I release it, the point is it won't go any higher than the original release point. Does that make sense to everybody? So if I release it from here, okay, then it will oscillate and it'll come up to here. It won't go past the point. Okay? Because of energy conservation, it can't go further than from where I released it. So it will start from here, it'll go down, it'll come up, it'll go up to this point, come back down, it'll come up to this point. So the initial displacement will actually be the farthest it can go. So that's why the amplitude will be x0. Does that make sense to everybody? Okay. It's kind of, it may be easier to understand from the point of view of the pendulum. If I start the pendulum from here, the ball won't go deeper. So this thing loses a lot of its use because I'm not holding it very steady. But the pendulum will not, if I start from here, the pendulum will not swing and then go all the way up to here. Does that that's the notion of an amplitude, the maximum point. And so we have that, so that x as a function of time will be x0 times cosine omega of t. Okay, any questions about this so far? All right. So we said, remember, we said omega is the square root of k over n. All right. But let's start. But let's keep writing it in terms of a, because a is kind of the general way of writing things. Okay. Now let's talk about the velocity. So the velocity, the instantaneous velocity, the x component of the instantaneous velocity, that's going to be the time derivative of x. Okay? So in order to get the velocity, I just need to take the time derivative of this, and we just learned how to do that. So Vx as a function of t. The a is out in front here. The cosine becomes a sine with a minus sign. Remember, the cosine gets the minus sign in front. Okay. Minus sign. But then there's also, I didn't leave enough space, there's also an omega, so I need to put that in there. Okay, so there's also the omega, and then sine omega t. So that's the velocity. Let me write this a little bit more neatly. Minus a omega sine omega t. Questions about this? All right, so then we can plug in, if we say that a is equal to the initial position, then we would get v sub x of t is minus x0 omega sine omega t for this particular case. Questions? Questions? All right. Now, sometimes they may ask you, what is the maximum speed? So the maximum value, maximum speed of the mass. Okay? So what is the biggest possible value that the sine function can have? 1, right? What's the biggest value that the cosine function can have? 1, right? By the way, if I ask what is the lowest value that the sine function can have, what would that be? Negative 1. Same thing for cosine. Right? So if they're asking for what is the maximum speed of the mass, then, you know, so cosines and sines are bounded from 1 to minus 1. So it's just going to be, let's look at maybe this guy here. Oops, you can't see that one. The maximum value for the speed, which is the magnitude of the velocity, will be a times omega. Does that make sense to everybody? Because the sine function is going between 1 and minus 1. It's this thing that I'm multiplying out in front that tells me what the maximum value would be. Okay. Everybody good on that? So for example, if a times omega is 2, then 2 times the sine function, the biggest it could be is 2. That's all I'm saying. Okay. So the maximum speed of the mass is Vx max is equal to a times omega. We don't need the minus sign because the speed is defined as the magnitude, so the minus sign goes away. Good. Okay, any questions about that? All right, so let me just copy down the formula again for the Vx. It's a omega sine omega t, sine of omega t. So let's write down the kinetic energy. Okay, so the kinetic energy of the mass, because it's moving, it has some kinetic energy. So the kinetic energy will be, there's no rotations here, it's just translational kinetic energy. It's 1/2 mv squared, or vx squared, if I want to be careful. Everybody's okay with that? 1/2 mv squared. So I have this ugly little formula for v. Let's square it, make it even more complicated. And so I have 1/2 m in front. Then I have a omega, but that gets squared. The a gets squared. The sine gets squared. Omega t. Okay, that's what the kinetic energy will look like. There's a reason why I'm doing this. We're going to do something with kinetic and potential energy and ask what the total mechanical energy looks like. Okay. All right, how about the potential energy? So we're talking about the spring potential energy. So anybody remember what was the formula for the potential energy stored in spring? 1/2, wait, what? Kx squared, okay? Kx squared, 1/2 kx squared. Okay, so let's write this out. 1/2 k. Now x is a cosine omega t. All right, I have to square it. Bear with me. I'm just writing a lot of ugly little formulas down. So I'll have 1/2 k a squared cosine omega t. Cosine squared omega t. All right. I have a formula here. I would like to try to make this formula look a little bit more, or either this one look a little bit more like this one, or this one look a little bit more like this one. Okay? So, let's see. It doesn't matter which one which. In my notes I do a certain way. So I have omega is equal to the square root of k over m. Okay, thank you. And so omega squared is k over m. All right. So I'm staring. Let's do it backwards from what I did in my notes, just to keep me on my toes. So omega squared is equal to k over m. Let's write this k over m. Okay. So let's rewrite the kinetic energy. Instead of writing omega squared, I'll write k over m. That's kind of nice because the m's cancel. Okay? And I get 1/2, and then I get a k. I get an a squared of a sine squared times omega, sine squared of omega t. Okay. Questions about that? All right. Now, maybe some of you anticipate this. I have potential, the kinetic energy is 1/2 k a squared. 1/2 k a squared times the sine squared of omega t. The potential energy is 1/2 k a squared times the cosine squared of omega t. What is the sine squared plus cosine squared the same angle? 1, right? Take any angle, sine squared plus cosine squared, any angle, it gives you 1. Okay. Where does this come from? This comes from the Pythagorean theorem, right? If you have an angle and a right triangle, right, one of the sides would be the hypotenuse times cosine, the other one would be the hypotenuse times sine. If I do the sum of the squares of the legs, I would end up, when you add them together, I get the hypotenuse squared. Right? But I'm sure you remember sine squared plus cosine squared equals 1. Hopefully that was. So if I add them together, I get this formula that the mechanical energy, the total mechanical energy, is equal to k plus u, which is going to be 1/2 k a squared, and then I'll have sine squared plus cosine squared. Sine squared plus cosine squared. And this guy is equal to 1. And so we get that the mechanical energy, the total mechanical energy is 1/2 Ka squared, which is kind of neat in that it doesn't depend on time. This is a constant. Okay. So if I release the mass from rest, from initial position x0, remember I said that A is equal to x0. So if you want to make a connection with that, just plug it in here. Are there any questions about this? So if I have a mass on a spring and it's oscillating, then the total mechanical energy of the system is a constant. It's 1/2 the spring constant times the amplitude squared. Now, so if I make a plot, I can make this little plot now. Plot of energy versus time. Energy versus time. Energy. Different kinds of energy. So here's my 1/2 Ka squared. That's going to be my E mechanical, the total energy. But then what will happen is that I have my my potential energy will look like this. It'll be a cosine squared function. That will be, this one will be du. And then my K will look like this. And it's kind of cool, those curves, when you add them together, they add up to a constant. Okay. These wiggles, they even each other out. Okay. Any questions? Pretty good. There's one last thing I want to sneak in because your homework this weekend talks a little bit about something called a phase angle. So let me just mention this. Yeah, we're worried I want to keep you too long. So let me do it from the notes so it doesn't I don't keep you too long past 3:45. Okay, so if the mass on the spring, if it does not start from rest, then what happens is that the function becomes a cosine omega t plus phi. So instead of just having a cosine of omega t, there's this extra piece here plus phi. And that's what's called the phase angle. Okay. Phase angle. So the only thing that changes now is everywhere you saw the omega t, you see the omega t plus phi. It's for cosine, you see it for sine, that's all. Okay. So everybody's okay with that? And then, so remember last time we plotted a cosine omega t? What it looks like is it goes from a, goes down to negative a, goes up to t. Okay, so capital T is the period. So we have the period is actually equal to 2 pi over omega. We derived that before. You can also write it in terms of the spring constant and the mass. The last thing I want to show you is what this guy looks like. A cosine omega t plus phi. It gets shifted backwards by time phi over omega. Okay? So if I have this extra phi here, it's shifted backwards by phi over omega, and it looks like this. This is the key concept I want to leave you with. That instead of having the cosine having a peak at 0, it has its peak at phi over omega backwards from 0. Everything gets shifted backwards by phi over omega. And so that's the case where phi is greater than 0. If you don't believe me, if you think I'm just making this up, it doesn't make any sense what this guy's talking about, you just simply write down the difference between omega t plus phi and omega t. Say omega t prime plus phi is equal to omega t. And then you solve for t prime, and you see it's t minus 5 omega, and that's why it gets shifted backwards rather than pushed forward by 5 omega. Okay? If that was a little too fast, the notes are uploaded. You can take a look at that. Have a good week, and I'll see you guys next week.
Which notes did you just